On a cold morning on the bluff above Fort Point, a man leaned over a brass instrument set on a tripod and waited for the fog to thin enough to see the cliff a mile to the north across open water. The instrument measured one thing only: the angle between where he stood and something far away. It could not tell him how far away that thing was. There was no beam of light to send across the water and time on its return, and no signal from overhead to read a position off the sky, because neither had been invented and neither would for another 30 years. Between him and that far cliff ran a strait that no tape could cross, and somewhere out in that water, at a spot nobody had yet marked, a tower would have to stand. What that man was fixing was the position of one of two towers that would carry a bridge across the Golden Gate, and the difficulty was that he had to be exact, while almost nothing about the site would hold still. He had to fix two tower positions nearly a mile apart, one of them more than 1,100 feet out in open water, while the current beneath it ran to several miles an hour, while the shipping channel stayed open to traffic, while fog closed his sightlines for days, and while the whole arrangement stayed exact enough that two towers built years apart would end up carrying cables that met, wire for wire, in the middle of the span. The bridge is usually remembered as a triumph of steel and orange paint. It was first a triumph of measurement. The steel could not be ordered, the cables could not be spun, and the towers could not be placed until someone had reduced a mile of moving water to a set of numbers and been right. This is the story of how a strait was measured with brass and steel tape. It is the story of the men who fixed two towers in the right place years before the cables that joined them existed. It is the story of one number, 4,200 feet, that had to be true before anything could test it. And the first obstacle was the oldest one in surveying. You cannot measure a distance you cannot cross. The obvious answer was a steel tape or a chain laid straight across, the most trusted tool a surveyor owned, accurate on solid ground to a fraction of an inch. It was useless here. A tape stretched across a mile of tidal water would bow in the current, sag under its own weight, and never lie straight, and the channel beneath it could not be closed for the attempt. The second answer was to take the tower positions off the nautical charts that already existed for the strait. Those charts were good. They were drawn to keep ships off the rocks, and for that they were precise to within yards. But a tower foundation had to be set to the foot, and its cable had to arrive at a partner tower a mile away and meet it exactly. So an error a passing ship would never feel would put the two halves of a bridge permanently out of line. The third answer was to measure from the water, from boats dropping marked buoys and ranging between them. At that time, it was hopeless. A boat has no fixed place to measure from, and the instant you read an angle, the boat has moved, and the buoy with it. Every direct approach failed for the same reason, that the water would not stay still and could not be crossed. So the answer was to stop measuring the water at all, and instead measure a thing that would hold still, a straight line on solid ground, letting the far point be reached by sight rather than by foot. That method was triangulation. Triangulation begins with a baseline, a straight line of known length laid out on firm ground and measured with a tape you can hold flat, check, and check again as many times as it takes. You stand at one end and measure the angle to the distant target. You walk to the other end and measure the angle again. Two angles and the length of the line between them fix the triangle completely, and simple trigonometry then gives the distance to the point you never touched. It is the same method that fixes the distance to a ship at sea by sighting it from two towers a known distance apart without any boat leaving the shore. The inversion at the heart of it is the elegant part. The width of the strait feet. The very thing that made a tape useless meant nothing to a method that measures angles instead of lengths. The far point stays unreachable, and you only ever look at it. What defeated every other approach was irrelevant to this one. The Bridge District understood this early and named a manager, Alan McDonald, years before the first concrete was poured in 1933. The $35 million in bonds paid for a project that began not with steel, but with angles. It existed on paper first. The main span between the towers was 4,200 feet. Each side span was 1,125 feet. Each tower would rise 746 feet above the water, and the deck would hang 220 feet above the tide. Every one of those numbers had to agree before a shovel moved. What carries the bridge is not the towers, but the two main cables that ride over their tops, each 7,650 feet long, running from one anchorage to the other. Each anchorage a block of concrete weighing 60,000 tons. The towers matter only because the cables rest on them. Set the tower tops wrong, and the cables ride wrong. Each cable is not one piece. The John A. Roebling Sons Company, which had spun the Brooklyn Bridge cables 52 years earlier, built each one from single wires carried across the strait on a wheel that ran back and forth, one loop at a time. Later, 6 at once, the strands color-coded so no wire was lost. A finished cable is 3 feet through, and it is made of 27,572 wires, each one less than 2/10 of an inch across, thinner than a pencil. Across both cables, there are 80,000 miles of wire. The work was scheduled for 14 months. Roebling finished the spinning in 6 months and 9 days. The wire is galvanized carbon steel, drawn hard for strength, and every wire in a cable had to sit at exactly the same sag as its neighbors. That sag was set against a single reference wire, strung first and adjusted to the computed curve, and every wire afterward was brought to match it. Steel lengthens in heat, so a wire matched in the afternoon sun and one matched at dawn would not agree, and the men had to read the sag against the temperature of the steel at that moment. There was no beam to fire down the line to check it. The curve was watched by eye against the reference wire and by transit sighted from the tops of the towers. If the reference wire was set wrong, every wire brought to match it would be wrong. If the wires were wrong, the cable would not share its load evenly. And if the load was not shared evenly, some wires would carry more than their share, and the safety margin the whole bridge stood on would quietly vanish. The entire structure came down, in the end, to a curve of steel judged against one first wire. Drafting table follows the structures that got built and the measurements the record left out, and there is more of this every week. What the arithmetic could not do was go down into the water. For that, men went instead. The bridge went up in the deepest years of the Great Depression, and the work drew men who needed it, thousands of them across every trade. The Pacific Bridge Company laid the foundations. The steel was raised by McClintock Marshall, a Bethlehem steel firm, whose iron workers stood the towers and rode the cables. The hardest working day belonged to the divers at the South Pier, more than 1,100 feet from shore. They went down as far as 110 feet into water that was dark, cold, and moving, and they could work only at slack water. The 4 brief turns of the day when the tide changed and the current eased. In that window, they set dynamite charges, cleared broken rock down to bedrock with high-pressure hoses, and guided the concrete forms by feel, because at that depth in that water, there was almost nothing to see. The sight punished them. Fog came off the ocean, and wind and cold for most of the year. The timber trestle out to the pier was struck by a freighter in 1933, and half of it was torn away by a storm soon after, and the men rebuilt it and went back out along it. The equipment they trusted with their lives included a safety net strung the length of the work, an idea Joseph Strauss insisted on, and hard hats, still new on a construction site. For most of 4 years the net held, and it caught 19 men who fell and lived, men who called themselves the Halfway to Hell Club. Then, on February the 17th, 1937, a scaffold carrying 12 men tore loose and went through the net, and 10 of them died. In all, 11 men were killed building the bridge. The pay ran from $4 to $11 a day. The payroll records the trades and the counts, and it keeps some names and loses many more. The surveyors and rodmen who fixed the angles and most of the laborers who cleared the rock below the water appear in the record as numbers and job titles rather than as people. Whether the pay was fair is not a question the payroll can answer, because the payroll was kept by the men who set the pay. Everything came to rest on a single test. The steel roadway was built outward from each tower toward the center, and the two arms had to meet in the middle. Every angle measured off that cold bluff years earlier now had to prove itself in the last few feet of open air over the strait. If the towers had been set even slightly wrong, if the 4,200 feet had been off, the two arms would arrive out of line, and no amount of steel could close a gap the arithmetic had already opened. The arms reach out. Each day the gap narrows. Overhead, the cables hold the curve they were computed to hold. The tolerance now is not in feet, it is in inches, and the arms meet. The number set years before, from angles measured across water nobody could cross, holds. On May the 27th, 1937, the bridge opened, and roughly 200,000 people walked across it on that first day. Joseph Strauss presided as chief engineer. Charles Ellis, who had done the calculations that turned the strait into the numbers that held, was not there. Strauss had removed him from the work in 1931, and Ellis received no credit at the opening. The recognition reached him decades later, long after the number itself had already been proven true. Within a single lifetime, the brass transit, the steel tape, and the long hand arithmetic were replaced. The laser, first built in 1960, could send a beam across the water that no tape could cross. Satellite positioning, decades later, could fix in seconds a point that had once taken days of angles and computation. The successor did in a moment what a crew had done in a season. What did not change was the idea underneath it. Before any large structure goes up today, a control network is still laid, a baseline still fixed, positions still computed outward from it. The satellite replaced the labor of triangulation, not its logic. The men on the bluff were doing by hand exactly what the machine now does without anyone watching. Stand today at the rail at the center of the span. You are 220 feet above the water, and the deck moves very slightly under your feet by design. Above your head, the cable runs 3 feet through, and packed inside it are those 27,000 wires, everyone brought to match a single reference wire strung before you were born. The spot where you are standing is exactly where it is, because a man on the far shore measured an angle to it and trusted the number it gave. When people picture San Francisco, or the engineering of that age, this is the shape they picture. The reason is not the color and not the postcard. The reason is that the thing was computed right the first time and has held ever since, through wind and fog and earthquake, exactly where it was said it would stand. The men who sighted the angles and stretched the tape and went down into the cold water are mostly unrecorded, and the work they measured into place still deserves the recognition nearly 90 years on. Not a leap of faith, not a lucky alignment, a mile of moving water reduced to a number, and the number was right.